Have you ever stopped to wonder why you can remember yesterday but not tomorrow? Or why so many things in our universe seem to be on a one-way track? Well, it turns out there's a fundamental law of physics that basically acts as the universe's clock, governing the very direction of time itself. So let's dive in and see what that's all about.
Okay, think about something you've seen a million times. You make a hot cup of coffee, you put it on your desk, and what happens? It cools down, right? It shares its heat with the room. But have you ever seen the opposite happen? A lukewarm coffee sitting there and suddenly sucking heat out of the air and starting to steam all on its own? Of course not. That would feel, well, it would feel wrong, impossible even.
Physics actually has a name for these one-way events. They're called irreversible processes. It's the same reason you can't unscramble an egg or unbake a pizza. They follow this strict forward direction. And what's really wild is that the reverse process wouldn't even violate the conservation of energy. But still, they just never, ever happen.
This one-way street that all of reality is on is so fundamental that it literally gives time a direction. We call it the arrow of time. But this isn't just some philosophical idea. It's dictated by a real, measurable property of the universe. So the big question is, what is this property? What law is acting like the ultimate traffic cop, always pointing forward?
The answer, it turns out, is found in one of the most important and maybe one of the most misunderstood ideas in all of science, the law of increasing entropy. So let's meet the star of our show, entropy. The easiest way to think about it is as a measure of disorder or messiness. You know, a perfectly organized, tidy room has very low entropy. That same room a week later with clothes and books everywhere, that's high entropy. And the key to this whole thing is that the universe has a powerful, unwavering preference for messiness.
And this isn't just a casual preference. It's basically a core rule spelled out in what's called the entropy postulate. It's a simple idea with enormous power. If you take any closed system, meaning nothing can get in or out, and something happens inside it, the total amount of entropy, the total disorder, will always go up. It never, ever goes down.
So let's go back to our coffee. When it's hot, the heat is nicely organized and concentrated in the cup. As it cools, that heat spreads out randomly into the room. It's become more disorganized, more dispersed. So the total entropy has increased. The only time entropy can stay the same is in a perfectly theoretical reversible process, which is a useful idea, but it's not something that actually happens in the real world.
And all of this gets boiled down to the mathematical core of the second law of thermodynamics. This little formula here just says that the change in entropy, that's what delta S means, in a closed system has to be greater than or equal to zero. It can go up, or in some perfect imaginary scenario, it can stay the same, but it absolutely cannot go down. This is one of nature's most fundamental rules.
Now, this isn't just some abstract concept for a blackboard. This law has huge, very practical consequences that put a hard limit on what's even possible in our world. And it all starts with the idea of efficiency.
Think about any heat engine, the one in your car, a giant power plant, it doesn't matter. They all follow the same 3 steps. First, they take in heat from a hot source, like burning fuel. Second, they use some of that heat energy to do useful work, like turning wheels. But, and this is the absolute key, they must, as a third step, dump the leftover energy as useless waste heat into a cooler place, like the air around us.
So why do they have to waste heat? Why can't they just use all of it? Because of entropy. Turning all that disorganized heat into perfectly organized mechanical work would be like tidying up the universe, decreasing entropy. That breaks the rule. So to satisfy the second law, the engine has to create some disorder. And that disorder is the waste heat it pumps out. This means a perfect, 100% efficient engine is physically impossible.
So what's the theoretical limit? Well, even for a perfect, flawless engine, something physicists call a Carnot engine, operating at temperatures you'd find in a typical car, the absolute maximum efficiency it could ever reach is only about 55%. And in reality, with friction, heat leaks, and all the other messy real-world problems, the actual engine in your car is probably only about 25% efficient. Think about that. 3/4 of the energy in the expensive gasoline you buy is just thrown away as waste heat. It's an unavoidable tax charged by the second law of thermodynamics.
Okay, so we know the law is unbreakable. But why? Why does the universe insist on things getting more and more disordered? Well, the deepest answer isn't about some mysterious force. It's about simple, staggering probability. To get this, we have to zoom way, way in.
Imagine a box full of gas molecules. The things we can measure, like its temperature or pressure, we call that the macrostate. But that macrostate is made up of countless microstates, and a microstate is the specific position and speed of every single molecule at a single instant.
And here is the crucial insight. Nature doesn't prefer any one specific microstate over any other. Think of it like shuffling a deck of cards. Any single specific order of the 52 cards is just as unlikely as any other. But there are vastly more ways to get a messy, mixed-up deck than there are to get a perfectly ordered deck.
Now look at our gas in a box. How many ways can you arrange the molecules so they're all crammed into the left corner? Well, there's basically only one way to do that. But how many ways can you arrange them so they're spread out evenly throughout the whole box? For just 100 molecules, that number is a 1 followed by 29 zeros. It's just an overwhelmingly, astronomically larger number of possibilities.
So this is the big reveal. The second law isn't a force, like gravity that's pushing things toward disorder. It's just a statement about overwhelming odds. A system doesn't get messy because it's commanded to. It just naturally wanders into the state that has the most possible arrangements, because there are just so many more of them. A messy state is simply the most probable state.
This whole profound idea was captured in one of the most beautiful equations in all of physics by Ludwig Boltzmann. In fact, it's engraved on his tombstone. It says that entropy, S, is directly connected to W, where W is simply the number of possible microstates a system can have. The more ways there are for something to be arranged, the higher its entropy. It's that direct.
And this brings us right back to the arrow of time, but with a final cosmic question. If the entire universe is one big closed system, then its total entropy must always be increasing. It's moving from a more ordered past to a more disordered future, toward an eventual state of maximum entropy. This is sometimes called the heat death of the universe, where everything is uniformly spread out and nothing interesting can ever happen again. So what does this law tell us not just about our coffee cups, but about the ultimate fate of everything?